Thank you for having me. It's an absolute pleasure to be back in Cambridge. I couldn't decide which projects to talk about because it really is an exceptional time. I am a big fan of the big spend era, wherever George is. In the Dark Energy Survey, my recleansing team is in the end stage of our final legacy analysis. And at the same time, our field is bracing for photometric measurements, maybe I shouldn't use the word bracing, anticipating photometric measurements from billions of galaxies from the Rubin Observatory. But I decided it would be most interesting to tell you about where we're stuck, rather than all the things that I think we're doing well. And that's really quite tactical because there's so much expertise in the room. Somebody will have the answer. But also fitting because most of the work that I'll talk about is done by graduate students who are here. So the context is that weak lensers are being fire-hosed with new data. So in the last decade, we've had 3 surveys turning out millions or hundreds of millions of galaxy observations. And we're in the process of analyzing our final data sets. So DES is the one that I spend most of my time on, and it is the most powerful of the 3 with 4 times the number of galaxies and the area of the other 2. Now, these surveys have produced state-of-the-art constraints. It's from the low redshift universe, and these results have been intriguing, and they kick-started a larger conversation in the field, which is the S8 tension. But really, they are mere training grounds for what is to come, and that's the surveys on the right. So the way I see it is we've had a decade to learn what we can about doing weak lensing cosmology, and now is the time to apply it. And the game has really changed. It is a high-precision probe for cosmology, and our task is just to have ultimate control on the systematics that are wildly dominating our power, our statistical power. And that's so we can get the most out of these surveys. So what are we actually measuring? The large-scale structure distorts the fabric of the universe, and the light path from background galaxies gets distorted on their journey to our telescopes. And we measure these distortions, which appear as coherent alignments for galaxies whose light has traveled past similar structures on their journey. We do this statistically, so we measure the correlation of shapes of galaxies, and that signal is because of all the distortions that the light has received on its journey past the large-scale structure. And to model the signal, we need to estimate how far away the galaxies are, so we know how much structure the light has passed through. But the key point is that these correlation functions are directly related to the underlying structure. So we probe this combination of parameters. We probe this combination of parameters, omega matter and sigma 8, and the best constraint that we can place is on this S8 parameter. Now, beyond the lessons that we've learned from these 3 surveys working in very healthy competition, the surveys have all turned up these persistent, intriguing, and mostly annoying results, which is known as the S8 tension. So none of these results disagree with any real significance. But from the very first cosmic share survey, we've seen a low value of S8, or less clumpy structure in our universe, compared to the prediction from the CMB or from Planck satellite. Now, my experience has been that there is a flavor of the month for the last 10 years on what is causing the weak lensing tension. So there's always a leading suspect. My take today is that photometric redshifts are pretty hard, but we do a good enough job for stage 3 surveys. We have relatively shallow surveys. We have our work cut out for future surveys. It's really tricky to measure the shapes of blobs of pixelated light, but we do that remarkably well now. Galaxies can be intrinsically aligned, and this looks like a lensing signal. I think we over-worry about that one, but I go back and forth. And the last aspect is what I want to focus on today, and that's baryon feedback. And I think the forefront challenge for our weak lensing cosmology right now is that we need accurate modeling of the power spectrum, including on small scales, and that means that we need to understand baryon feedback extremely well. And at best, this challenge will severely limit our power in weak lensing surveys, and at worst, it significantly biases our cosmological constraints. Now, so this is the problem. The hydro simulations are increasingly more sophisticated, and they do a fantastic job of realizing a range of galaxy properties and processes. And the most important one for us is AGN feedback. They eject baryons beyond the virial radius for groups and clusters, and they redistribute the matter on small scales for us. And so that's suppression of the power spectrum. So I'm showing here the ratio of the full power spectrum to the dark matter only power spectrum. you can predict that suppression from the hydro simulations, and this plot is our problem. This spread is far too large for us to tolerate as an uncertainty. So there is still a very large range of amplitude and extent, scale extent of scenarios predicted by the simulations. Shopping around as a cosmologist, we just can't really tolerate this going forward. So our approach in DES has been, we're not going to think about that. We just want to test fundamental physics. We're going to throw away all of our small-scale measurements. So what I'm showing now on the top right is 3 panels from 20 that we have in our DES cleansing measurements. And the blue shaded regions we toss. And this is obviously a huge cost in constraining power for our survey. If we knew astrophysics perfectly, so if we could model intrinsic alignments and baryon feedback perfectly well, we would do more than a factor of 2 better with our stage 3 surveys. Now, if we try to model the feedback, I think this plot really demonstrates why this can be extremely dangerous. So this is one of the newer models on the market, the Halo model approach. And the model is sold as the dark blue constraints. It is calibrated to the Bahama simulations, and you can use that prior in the model in your analysis. But if you open up the prior and say, we don't want to rely on just one simulation, you get the light blue contours. So when you choose a simulation, you are directly choosing or pinning your value of S8. And we don't want to do that. Now, with work that I've done here with George and with Calvin, we've gone as far as to argue that this challenge of modeling feedback could even entirely be responsible for the S8 tension. So we sat for some months and investigated all of the new cosmological measurements that were coming out, pointing to low S8 results or high S8 results. And we tried to dig through and understand what was happening. And in the end, what we landed on is that the conversation needed to be flipped. We always talk about this as an early universe versus late universe tension. And really what we think is happening is a linear scales versus nonlinear scales tension. So it's just which axis on this plot you put your problems. Yes, great. Yeah. So we proposed a nonlinear solution to the S8 tension. And what I'm showing on this plot here, it's a very simple model, and I won't go into it. But if you just say, OK, Planck, BAO, they all work pretty well on linear scales. They look like lambda CDM. Let's just use the weak cleansing to tell us about the nonlinear scales. Then this is what you need to do. You need to suppress your power on small scales. And this is what the surveys tell us is the suppression that you need to solve the S8 tension and to reconcile all the cosmological observables. Now, fantastic. We've heard from people like CARE about their range of models on the market, for that matter, that do this. Great. The problem is many other things do this. So it could be that we're just not understanding baryon feedback. Now, with Leah Bigwood, who's another grad student here, we wanted to dig into these newer models for baryon feedback. So we said, OK, let's not throw away the measurements. Let's try and model them with the newer approaches. So we tried 3 models. The top one is the DES scale cuts, which rely on a simulation. Then there's this Halo model approach. There's an emulator built on a suite of Antley simulations. And there's an analytic model that's very flexible and can reproduce a range of simulations. And since the top 3 rely in some way, indirectly or directly, on X-rays, we use the bottom most flexible model with another probe of the gas, and that's KSE, which we just got a really nice explanation of. I just wanted to add on top of that the key thing that we care about here is that the KSE is very complementary to the X-ray. It tells us about the outskirts of galaxies rather than within the virial radius, and this is why we were attracted to it. Now, here are our results. What are the things that you should take away? Well, the first thing that I take away is that you can change your uncertainty on S8 by a factor of 2, not what we want. And you can change your value of S8 by about 2 sigma, also not what we want. But if you look at it a little closer, the green and the blue lines or constraints, they are the ones that are informed by X-rays, and the bottom constraint is what's informed by something else. And so this is where, it starts to, we can't really tolerate this model or prior dependence, and starts to ask questions or raise questions of the consistency of different views of feedback from X-rays versus from KSC. Now, here's the most intriguing part. If you turn things around and use your weak cleansing plus KSC to constrain the astrophysics, we can constrain the suppression on the matter power spectrum. So not now, and compare it to the predictions that come from simulations. And what we see is that the weak cleansing and the KSC both prefer a more extreme feedback scenario compared to the state-of-the-art hydrosimulations. To compare better to the X-ray data, so many of these simulations, the most important observation that they benchmark to that's most relevant for the power suppression is X-ray gas fractions. So here we're looking at the baryon fractions, and the black hatch line are from X-ray data. And we see that we get pretty good consistency at high masses where there is X-ray data. And once you go to lower masses, we think that the gas should be expelled further out. These masses, halos, should be emptied. Now, overall, we see that in our PK or our baryon fraction or our gas fractions, the weak lensing and the KSE are pointing to this consistent picture of more extreme feedback than the simulations and the X-ray data are suggesting. And we also see that impact on our cosmological inference. It's not necessarily surprising that the weak lensing and the plus KSE might give a different result to the X-rays. We're looking, X-rays tell us about the inner regions of halos, and now we're looking at few times the R500 radius. Is it that we're not expelling gas far enough out in our simulations? And there's also a mass and a redshift mismatch. We're looking at lower mass halos at higher redshift in both the weak lensing and the KSE, and the X-ray telling us about the very low redshift universe and the most massive objects. So I'm extremely excited about the future of using weak lensing and KSE to benchmark the simulations. Now, one more thing that I wanted to say is that you can ask a lot of questions about the model that we've used here. It is a flexible model, but it's still, maybe there's something unphysical in the model causing this. And most recently, I've teamed up with Ian McCarthy to use his flamingo boxes, which are very large, to go in directly and measure the galaxy-galaxy lensing and measure the KSE and establish these new measurements as a new benchmark, a new way to calibrate your simulations. And what we see is consistent with what we found with our analytic model. We use the lensing to pull out the mass sample that's relevant, and these are from previous lensing measurements that I've made in the past. And then you compute your KSE profiles. And in fact, we rule out the flamingo standard model to 7 sigma with the KSE observations. And the best fit that we can get is if we use the most explosive flamingo model, which is 8 sigma deviant, when you calibrate to 8 sigma different X-ray gas fractions. So there is some very clear mismatch happening between X-ray calibration and KSE or weak lensing calibration for baryon feedback. Now, if we are able to pin down feedback, the power of Rubin will be phenomenal for weak lensing. So in Calvin's most recent work with George and I, he proposed that the way that we should be using weak lensing is not just to constrain this S8 parameter. We're piling up all these different scales of cosmological information. Instead, what we should do is reconstruct the power spectrum. And you can see quite clearly here, these purple constraints are from Rubin year 10, that we will have this amazing power to tell us about the power spectrum and the cosmology on a range of scales, from linear to nonlinear. If we do have really good priors on our baryon feedback, we can use these constraints to tell us about dark matter. So here's different masses of axion dark matter, and we will have the power to distinguish between those with weak lensing from Rubin. So I'll wrap up there. You know, we're trying to answer this question of, does the standard model of cosmology accurately describe the universe, not just at early universe and late universe, but on linear scales and nonlinear scales? We think that you can resolve the S8 tension with this nonlinear solution, but what source is it? Is it extreme feedback? We must pin that down before we can say it's something more exciting. That leads us to start asking provocative questions like, do we have a consistent picture of feedback? I would say our observations at face value are telling us we don't. And we really need to pin that down to not severely limit our power of stage 4 weak lensing. Thanks.
Thanks very much, Alex.